Hello and welcome back to Everybody Codes 2025. For day 8, we're working with string art made using strings and a bunch of evenly spaced nails along a circle. So we have a circle and nails evenly spaced along the circumference, and then we number the nails in sequential order. So for example, this diagram shows what it would look like if we have 8 nails, and then to create the string art, we start with the string at a number, and then we thread the string around each of the nails in the notes sequentially. So for example, in this example, we start at 1, and then we move the string to 5, and then we wrap it around and bring it to 2, and then we wrap that around to 6, and so on and so forth. And so we're asked here, how many times does this thread pass through the center of the circle? So the input is fairly straightforward this time. Let's define a nails variable because the value changes depending on if you're doing the example or doing the actual problem. So to determine if the thread passes through the center of the circle, basically we're just asking, are there two consecutive numbers are exactly 4 apart. Because the circumference of this circle is 8 nails, that means that 2 points across the center from each other will be 4 positions apart. And so what that means is if we subtract the bigger one from the smaller one, we should get exactly 4, or more generally, half of the number of nails. So again, we can use this zip thing I introduced in a previous video to loop through the neighboring pairs. Basically what this is doing is it's taking the number list and the number list offset by 1 and returning the columns, which gives us the adjacent pairs. And then we want to subtract the smaller from the larger one, which we can also do by just taking the absolute difference. So if the absolute difference is equal to half of the circumference, then we add to our total count and output it at the end. Right, I meant to divide by 2 there. Don't know how I messed that up. Okay, and so that works fine for part 1. For part 2, we're now asking how many times we need to tie a knot, and the rule is each time we cross threads, we have to tie a knot. So basically, if a thread passes through another thread, we have to tie a knot. And so we see in this example that if a thread passes through 2 threads at the same point, we still need to tie 2 knots. This makes it a lot easier because it means we don't have to try to encode the positions of the knots. We just have to count how many times a thread crosses another thread. And so the way we can do this is each time we add we keep track of which threads already exist, and then each time we add a new thread, we check with the previous one. Now, how do we determine if a thread intersects another thread? Well, if we use our example with 8 nails, we can see that if we have a thread that already exists and a thread that's being added, they will intersect if one of the points is on one side of the original string and the other point is on the other side of the original string. And so, because one of these 2 values will always be larger than the other, we note that 1/2 of the arc is larger than the small one and smaller than the large one, and the other half of the arc is everything else. So basically what we're asking is it the case that, let's call these anchor points A and B, and the points that we're trying to add X and Y. basically what we're asking is it the case that x is between a and b and y is not between a and b, like so. And so what we can do is keep track of the strings that we already have. And then for each string, now this isn't the most efficient, but the input is not large enough that we need to be too concerned with optimization at this point. If we print the number of we can see that there are 3,000, which isn't the smallest, but checking every string against every other string would be 9 million here, which is completely fine for problems like this. So, in order to check, first we note that if either of the points are the same, then there's no knot that needs to be tied. And so to make our logic a bit easier, we'll just skip those cases. So if x is a, or x is b, or y is a, or y is b, then we can skip this one. Otherwise, we'll note that each point either has to be less than b and greater than a, or it has to not be. And so a string intersects if this condition is true for x and false for y, or vice versa. Which means that we can say if a less than x less than b is not equal to a less than y less than b. So this might seem a bit strange at first, but essentially what we're doing is we're comparing two Boolean values, where the first one is asking, is x to the right side of the string? And the second one is asking, is y to the right side of the string? If these are equal, that means they're either both on the right side, in which case we have no intersection, or they're both on the left side, in which case we still have no intersection. So if these comparisons are unequal, then we increase our total intersection count by 1. And we can see that it's not instant. It also doesn't work because I forgot that for this section the number of nails is 32. Actually, that doesn't make a difference here. Yes, it's because I forgot to consider that A could be larger than B, which would cause this to always fail. For ease of representation, we'll store the strings. We'll store the strings with the smaller value first. So like that. And we'll see that that works fine for part 2. Finally, for part 3, we are being told that the string art has been adapted to create magical symbols, and a special pattern is marked on the knight's shields that can be activated by cutting through the symbol using a sword. And it must be done in a way that goes from one nail to another, and we have a greater effect if we cut more threads. So we're asking, what is the best cut to make, and specifically how many threads are we able to cut with one stroke? Now for this one, the initial approach I tried was to again store all of the strings and then simply check every possible sword stroke and check how many threads that would intersect. That would work, but it isn't the most efficient. In fact, it takes quite a while to run. A slightly different brute force method that is somewhat better, at least I think it was, is instead we check each string and then increment the counter for all of the possible sword strokes that would cut through it. So basically, rather than looking at 2 to 8 and then checking which strings it cuts through, that's slower because it requires a lot of comparisons. Whereas if we are looking at the thread from 1 to 7, we already can easily iterate through all of the sword strokes that would cut through it, because like we established, we're looking for sword strokes where one point is on the right side and one point is on the left side, which means that we can just iterate through the possible values. So if our thread is from 1 to 5, those values would be 2, 3, and 4 for the left side, and 6, 7, 8 for the right side. Or I guess I got this backwards. So let's give that a shot. It's still not going to be efficient, and so I'll go over an optimization at the end. So now we're just keeping track of the strings, and we'll note that for this part, the input is substantially larger. And we'll note that I believe we have quite a few duplicates. I guess we don't have duplicates. Okay, I guess we do not need to worry about duplicate threads here. Okay, so we'll just keep track of all of the strings, and instead of storing the strings, we'll store a map from each cut to the number of threads that it would cut through. And we'll build this by iterating through the strings rather than iterating through the cuts, although it still won't be efficient either way because we're still doing a lot of iteration. So we established that one of the halves is going to sit between x and y, so we can sort the two values like so to just keep them in consistent order to make things easier for ourselves. And then we can say for left side in range from a plus 1 up to and excluding b. For example, if a and b are 1 and 5, then this iteration would go 2, 3, and 4, which is all of the points on one side of the string. And then the other side is going to be everything greater than b and everything less than a. So for stuff that's greater than b, we have range b plus 1 up until and including the number of nails. And for everything below a, we have everything starting from 1 up to and excluding a. And so we can join these together using the Python splat operator, which basically lets us unpack a value into a list. So we'll unpack this range into a list and then also unpack this range into a list, which will basically dump them both into one flat list of numbers. And so then we can do x, or I guess not x, like qr equals sorted left right, so that we keep the cuts in order as well to avoid counting 2, 6 and 6, 2 separately. And then we can do cuts qr equals cuts dot get qr, and if absent we return 0, and then we add 1. So yeah, not very efficient, but this will work. And then at the end we just care about which cut is best, so we'll just max all of the values. And so while I let this run, and it will hopefully return the correct answer, we can discuss how we can optimize this. So we are storing all of the cuts, and essentially we have a map from a coordinate, because it's a pair of two numbers, to a number, which means that we basically have a grid. And so we can instead store this value in a grid. And so using the simplified example, yeah, so this does take a while to run, but it will eventually return the correct answer. So this does work fine during the contest, but for the sake of a teaching point, let's optimize this further. So we basically have an 8x8 grid with numbers representing how many threads each cut will cut through. So for example, we see here that the best cut is between 3 and 7. And so if we number both axes, what we've basically determined is that we have a grid where the number in each grid tells us how many threads would be cut if we cut between these 2 points. Now the reason that's relevant is because let's consider what we're doing when we loop like this. We're looping a left point from some range to some other range, let's say from 4 to 7, and we're looping a right point from some range to some other range, let's say 1 to 2. That means that we're increasing everything in a rectangle by 1. And so the reason this takes so long is because each time we look at one of these threads, we're making an operation that is somewhere in the range of about 128 by 128. That's a lot of values to loop through and a lot of values to set in the grid. But what if instead of setting all of the values, we instead represent the position of the rectangle? And how we can do that is using a two-dimensional difference array. Let's take this into one dimension first and consider how we could store an array if we are making a bunch of operations that involve adding 1 to a range and then only reading through the whole value once. So let's say we start with an array of 5 zeros. And we want to repeatedly make operations that are somewhere along the lines of add 1 to all of these numbers. If we just store it as a regular array, this is rather slow because each time we have to modify up to 5 values at once. But if instead we store the difference between each of the values, then each time we want to add 1 to a range, we're only increasing the difference between the start of the range and the value before it by 1, and then decreasing the value between the end of the range and the value after it by 1. Which means that no matter how long the range is, we're only making 2 changes each time. And so in this example, if we store a difference array, then if we want to add 1 to all of these, and then 1 to all of these, we'd get something that looks like this. Wherein the first operation adds 1 to these elements, and so we increase this difference by 1 and decrease this difference by 1, and then this operation increases the last 2 values, so we increase this difference by 1, and then we don't care about the last difference. Finally, what we can do with our difference array is sum it cumulatively, which gives us this, which is exactly what we would have had if we actually modified each range individually. And so we can extend this to 2 dimensions. So suppose we have a grid of 4x4, and we want to be able to modify this rectangle by adding 1 to all of the values. We're going to take the top left corner and increase it by 1, which will increase every value below and to its right. And then to cut off any values from the right, let's expand this grid a bit so we can have our range in the middle. Once we get to this point, we want to stop the range of this rectangle, so we'll set this difference to a -1, and likewise on this side we'll set this to a -1 as well. And so if we try summing up everything by first summing column-wise and then summing row-wise, what we'll get is, when we sum here, we go 1, 1, 0, and then 1, 1, 1, 0. And so let's try this out. We sum column-wise first, and then we sum row-wise. Or... sorry, I did something wrong here. Ah, right, yes. Well, I forgot to sum this value column. So it's important that we first sum the columns, then the rows. We can't sum the values concurrently like so, otherwise we'd get something like this, which is what you want to do for Pascal's triangle, but not for not for two-dimensional difference arrays. So if we first sum all of the columns, then we get this. And then we sum up the rows to get this. Now you'll notice that didn't quite work because of this extra -1, and that's because it is receiving the cancellation factor from both the row and the column. And so in order to offset that, we'll re-add an extra 1 to avoid the double cancellation, and so the final result would look something like this. In the top left corner, we place a 1 to influence the rest of the rectangle, and then here we place a -1 to cut off the range of the rectangle, and then finally here we place a 1 to offset these two rectangles overlapping. So that might not have made immediate sense first, but hopefully it'll make sense once we actually implement it. So we'll store a difference array, which will be a nails by nails size grid. And then let's define a helper function to help us do this more easily. So we'll find a function called add, which will increase the values within a rectangle by 1. So first we'll want the top left corner. So let's call that row 1 and column 1. And then we want the bottom right corner. We'll call that row 2 and column 2. And so we first need to establish what we're actually going to pass through to this. And what I'm going to do is make it inclusive in the range of nails. So for example, if we are trying to, let's redraw the nails diagram. Let's say we're trying to add up all the cuts, add 1 to all of the cuts that would cut through the thread 1, 4. Or, for example, let's pick let's pick 3, 6. And the reason I'm picking 3, 6 is so that way the left range isn't contiguous. So what that means is we're going to need to increase all of the values in the rectangle from 1, 4 up until 2, 5. And then we're also going to need to increase the values in the range from 4, 5 up to 7, 8. And the reason we're doing it that way is because, again, keeping the values ordered from small, like keeping the cuts ordered from the small point to the large point helps us avoid miscounting. And so the values we're going to pass through to the add function in this case would be 1, 4, 2, 5, and in this case would be 4, 7, 5, 8. So because our difference array is 0 indexed, because it's Python, and the nail positions are 1 indexed, we're going to need to offset the first row and the first column by -1. Now, one thing to note here is that we can add some sanity checks here to avoid invalid values to make it easier when we eventually call the function down here. So what I mean by that is if we were doing the thread from 1 to 4, then 1 minus 1 is 0, which doesn't exist. So we'll skip that. So what that looks like here is if R1 is less than 1, then we'll skip it. And if C1 is less than 1, then we'll skip it. Likewise, if we were looking at the cut from 2 to 8, then we would also try to do everything to the right of 8, which would start at 9. So if R1 is greater than the number of nails, we'll skip. Or sorry, if R2 is greater than... No, it is R1. And if C1 is greater than nails, we'll skip it. And so now looking at the example of 1, 4, 2, 5, if we refer to our original grid, 1, 4, 2, 5 would be this range here. Or I guess since we're doing rows first, it would be like so. 1, 4, and 2, 5. And so the top left index into which we're going to place the 1 is going to be at position 0, 3. Which makes sense because, again, these values are being 1 indexed. So we're going to do difference array at R1 minus 1 and C1 minus 1 will be increased by 1. And then we'll need to place a minus 1 here, which is at index 0, 5, which is going to be C2. And then likewise, we'll modify this corner. And finally, we'll modify this corner, as we mentioned before, to offset it. Finally, one last sanity check is that we'll note that sometimes R2 and C2 can be out of range. And so if they are, we'll just skip it. So if C2 is less than the number of nails, we'll set it, and if it's not, then we'll just ignore it. Because if the rectangle is at the edge of the board, then there's nothing past it that we actually care to adjust the offsets for. And so we can see now that for each add operation, we're always performing a constant number of actual modifications to our difference array. Finally, we just need to determine how to modify the values here. And so we'll note that we always want R1C1 to be less than R2C2, which means that we're going to still need to split our range into 2 parts. One of them is going to be with everything between A and B as the first point, and everything to the right of B as the second point. And the other one is going to have everything to the left of A as the first point, and everything between the two as the second point. And so that add operation will look something like this. In this case, R is referring to the first cutting point, and C is referring to the second cutting point. And so R1C1 is the lowest cut in terms of the 2 nail positions, and then R2C2 is the highest cut. And so the lowest cut that we can do is to start from A plus 1 and B plus 1. And then we'll end at B minus 1 and at the maximum value nails. And then for the second one, the lowest value we can do is to start at 1 and A plus 1, and the highest value is A minus 1 and B minus 1. And so we can see that each add operation is a constant number of operations on the difference array, and each string introduces a constant number of add operations, which means that overall this is just linear to the number of strings and doesn't involve the size of the circle as a factor. Finally, we can sum up the array like so. Guess we actually don't need to name it separately. We'll tally it up by first summing row-wise. So for R in range nails and for C in range nails, we will add the value in the previous row to the current one. So cuts are C plus equals cuts from the previous row, R minus 1 C. And since we obviously don't want to add the last row's values to the first row, we'll start at index 1. And then likewise, we'll sum each value, we'll add each value to the one to its right. And finally, we just need to take the maximum across both dimensions to get the value for part 3. So you'll notice now that this runs instantaneously. So let me briefly recap what I did here because I know it was quite a bit. the first observation is that rather than checking each cut and seeing how many threads it cuts through, we can use each thread and calculate which cuts would go through it, as that avoids needing to do the comparison each time because it's easier to generate the values. And the second optimization to see is that we can use a difference array. So again, as a quick recap of that, instead of storing the actual values, we store the difference between each pair of values, which means that if we want to modify a range, since that only modifies the differences at the start and end of the range, it changes our linear operation to a constant operation and just requires us to do a single cumulative sum at the end. This works just as well in 2 dimensions, but we do have to add an extra factor here to offset these two values adding up. And finally, the remainder of the logic here is just a bit of being careful with one-offs and making sure that we're starting at the exact correct position. I'm actually surprised that this works, because I forgot one last note, which is that if we cut along a thread, it also gets cut, which I actually completely failed to consider here, and in my previous implementation. So we would need to add the possibility of cutting through the thread directly. I got lucky in that it doesn't change my answer here, but I suppose I would have noticed this issue if I was trying on the test case. So yeah, if I remove this line, then it would give me an answer of 6. So I would have noticed the issue if I tested it first, but I got lazy here. So yeah, good to note that that is explicitly specified in the problem statement. In any case, that's all for this part. Very interesting problem. I got stuck on part 3 for quite a while. Somehow I managed to mess up both not changing the 8 to a 256, which impacts the entire solution, and also I forgot to update the input file from between part 2 and part 3, so that cost me quite a bit of time, and then I had weird one-off issues and other stuff like that for quite a while. So I think I got probably the most wrong answers out of any problem of this style I've done before, even compared to all of the previous Advent of Code problems. Even in the later days, I don't think I've messed up quite so many times. So yeah, it took me a while to get there, but we got there in the end. Thank you for watching, and I'll see you tomorrow.